In this video, we're going to talk about bias variance trade-off in machine learning. This comes to you through my YouTube channel AINEXUS and the playlist course on ML. My name is Dr. TV Geeta. So the learning objectives are to define bias and variance in machine learning, explain underfitting, good fit and overfitting, understand the bias variance trade-off, identify how model complexity affects bias and variance, and apply techniques to reduce generalization error. So the bias variance trade-off, this is a core problem in machine learning. So why do some ML models underperform? Because they fail to learn the important patterns in the training data, they fail to ignore random noise in the data, and they fail to perform well on new unseen data. The central challenge is if the model is too simple, you have high bias and underfitting and it misses the pattern. If you have too complex, then you have high variance, overfitting, and it fits noise in the data. So you have to have a good fit, balanced fit, which captures the pattern and generalizes well. What is bias? Bias is error from overly simplistic assumptions. So definition of biases, it is the error introduced and a model makes strong assumptions about the relationship between input and outputs. Example, suppose the true relationship between advertising spending and sales is curved or non-linear, and you assume a linear model like sales is equal to beta 0 plus beta 1 into advertising. It fails to capture the nonlinear relationship. So high bias characteristic is model is too simple, misses important patterns, training error is high, testing error is also high, and this usually leads to underfitting. So analog is trying to describe a complicated landscape using a straight line. Result is consistently wrong predictions even on new data. Now, what is variance? Variance is sensitivity to the training data. High variance model changes a lot when the training data changes slightly. So high variance characteristics, model is too complex or too flexible, learns noise along with the pattern. So the training error is very low, but the test error is high. So this leads to overfitting. Example of logistic regression is shown here. So you can have a linear one where you have high bias and a very flexible model where you have high variance, and a balanced model, it's a good variance with the data points. Now, analogy, a student memorizes every question on one practice exam, but struggles when the questions change. The result is predictions are unstable and don't generalize well. So there is something called the Goldilocks zone of machine learning, which is a good fit we need to get. So how do we find this goal? It should not be too simple model, should not be too complex, it should be just right for real world success. How to find that Goldilocks zone or sweet spot? Use cross validation to evaluate models, monitor training versus testing error, tune model complexity using parameters, changing parameters or features, choose the simplest model that works well, and then aim for the Goldilocks. Not too simple, not too complex, just right for real world success. Now, let's understand this a little more using analogies. So, let us understand bias and variance. So, high bias with low variance, darts are close to each other but far from the bullseye. So, consistent but wrong. Next, you have low bias and high variance. Darts are spread out but on an average close to the bullseye. Unstable predictions. Then you have low bias and low variance. Darts are close to each other and close to the bullseye. So that's the ideal situation. High bias plus high variance. Darts are spread out and far from the bullseye. That's the most worst situation. So we want our darts to hit the bullseye consistently. So a good model hits the targets reliably, not just once. So good generalization happens when our prediction is both accurate and consistent. Let's take another analogy. Here we have high bias and low variance, which is underwatering. Too little water every time. So plants don't get enough. Next is low bias and high variance. This is inconsistent watering. Sometimes too much, sometimes too little. Plants get inconsistent care. The next is low bias, low variance, just right amount of water every time. So plants grow healthy and strong. And the next is high bias, high variance, overwatering. Too much water every time, plants gets drowned. So what we have to understand here is a good generalization happens when a model performs well on new data again and again. So we are bringing one more aspect, which is consistency. It should be accurate as well as consistent. Why is it called a trade-off? Increasing the model complexity improves one thing, but sometimes hurts another. So if bias decreases, when the model becomes more flexible and can capture more patterns, the increasing complexity reduces the test error. But after a point, when you increase the complexity, it increases the test error. So that point, optimal complexity point, is what we need. So it's a balance act between bias and variance. The challenge is to find the sweet spot where bias is low enough and variance is also low enough to minimize the total error on new data. So good models don't just fit the training data, they generalize to unseen data. Now, let's take an example of a polynomial regression to understand this, how the model complexity affects bias and variance. Task is to predict house prices based on house size. So you could assume it's degree 1 polynomial, given here y is equal to beta 0 plus beta 1x. It's too simple. It cannot capture the nonlinear pattern. Next is degree 3, where we have y is equal to beta 0 and so on. This is just right, captures the underlying pattern well. Now, you may think, if I increase, what happens? You can increase degree to 20, but it's too flexible, follows the noise and random fluctuations. So this is the problem. Low training error does not mean it's a better model. Better generalization comes from the right balance of bias and variance. So how do we reduce bias? When a model is too simple and misses important patterns, that's when bias happens. You can increase the model complexity. Use a more complex model that can learn more flexible relationship, increase decision tree depth, for example, or use a more flexible model, add useful features, provide the model with more relevant information to learn from. For example, housing price problem, you can add location, bedrooms, age, distance to city center, etc. Use use a more flexible algorithm that can capture nonlinear relationship like linear regression, polynomial regression, for example, decision tree, SVM, and so on. And reduce excessive regularization. Too much regularization can oversimplify the model. So decrease the lambda in ridge and lasso regression. We have not gone into that, but so here lowering bias helps the model learn more from the data, but be careful, it may increase variance. Okay, next comes how to reduce high variance. So collect more training data. So add more images to a cat versus dog data set, for example. Simplify a model. Use a linear model instead of a high degree polynomial. Apply regularization. Use L2 regularization, ridge in regression. Feature selection. Remove customer ID from a churn prediction model because it is not going to affect the result. Use cross-validation, most probably 5-fold cross-validation, so that you can choose the maximum depth of a decision tree. We have not gone to decision tree. You will understand it later. Use ensemble methods. There are some methods so that you use a number of trees instead of a single decision tree. And you can also reduce the decision tree depth, say to a maximum of 3, so that you prevent the model from memorizing noise. So prevent the model from being too sensitive to the training data and improve generalization. So the total prediction error can be written like this. Expected test error is bias squared plus variance plus irreducible noise. So bias squared cannot capture the pattern, error caused by incorrect assumptions. Variance error caused by sensitivity to the training data. We've seen this. There is something called irreducible noise also. Random variation that no model can completely eliminate. So these are the issues. So what you have to do is total error cannot be reduced below the level of irreducible noise. Our goal is to minimize bias squared and variance as much as possible so that you get the best generalization. So bias squared decreases, the model becomes more flexible and captures more patterns. We've already seen this. So the total error is sort of U-shaped. Okay. So there is an optimal point. That is what we have to do. Find. So more complexity reduces bias but increases variance. The goal is to find the sweet spot, which we have already discussed. Only thing we are talking about bias squared here. So choose the model that gives the minimum test validation here. Thank you. Now we'll look at the summary. Bias, error from overly simple assumptions. Variance, error from being too sensitive to training data. High bias is underfitting, high variance is overfitting. Trade-off is balance bias and variance for better generalization. Goal is to minimize the error on unseen data. Now references are given here. These are some of the short questions and the descriptive questions. These are some of the problems I've given you so that you can understand these terms better. And thank you. So please do subscribe to my YouTube channel AINEXUS and especially the playlist Course on ML. The next video we'll be talking about K nearest neighbor algorithm. So we're starting on algorithms, working principle, distance measures, and so on. So thank you.